Have you ever imagined the universe not as a collection of stars, but as a vast web, threads of matter stretching across unimaginable distances, connecting galaxies like beads of light on invisible strings? Most of what holds the cosmos together can't be seen, yet it shapes everything we know. It's quiet, patient, and astonishingly precise. Astronomers call it the cosmic web, the hidden skeleton of the universe. Tonight, we'll trace those unseen filaments, from the faintest hints in background radiation to the grandest maps of galactic structure. If you enjoy exploring the calm, factual side of cosmic wonder, a small like or subscribe helps this journey reach others who listen the same way. Settle in. Let's uncover the invisible framework that holds the universe in place. Right after the Big Bang, the universe was almost the same everywhere. Smooth, even, and hot. The only differences were tiny, small changes in density, so slight they were easy to miss. Gravity began to act on those small differences. It pulled very gently, then a little more, and over long stretches of time it gathered matter into faint outlines of structure. With billions of years, those outlines sharpened. They became long filaments and rich clusters spread across distances so large that light needs hundreds of millions of years to cross them. This is the cosmic web. We cannot see it directly with our eyes. It behaves like a framework inside the universe, shaping where matter collects and where it does not. Without that hidden framework, galaxies would have no guide, stars would not come together, and the conditions for life might never appear. For most of human history, this network was unknown. Only in recent decades has it started to come into view. Astronomers built wide surveys, mapped how galaxies are arranged, and ran large computer simulations. A pattern showed up again and again: threads, nodes, and open spaces in between. The result looks ordered rather than random. It suggests that emptiness in space is not truly empty. It still follows rules and holds traces of matter and gravity. Shapes and connections exist even where things seem bare. The path through this subject runs from the smooth early universe to the pull of gravity that tightened the first threads, to the maps and models that let us infer what our eyes cannot see. There are meeting points where many galaxies gather. There are vast regions with very little inside. Together they form a single structure that stretches across the observable universe. A quiet question sits in the background as we think about it. If the cosmic web guides what we can measure, it may also guide things we have not yet learned to notice. The beginning of this story is stillness. Right after the Big Bang, the picture is not an explosion that throws pieces in every direction without order. It is a hot, dense, fast expanding soup of particles, light and energy spread evenly through space. Conditions changed quickly, but the overall pattern stayed remarkably uniform. If a very sensitive thermometer could have been placed anywhere then, it would have read almost the same temperature in every direction. That uniformity is one of the striking facts of early universe physics. The differences were tiny, about 1 part in 100,000. Imagine a sheet pulled tight across a frame. To the eye, it looks flat. If your touch was sensitive enough, you would find faint wrinkles. Those small wrinkles became the seeds of everything that followed. Stars, planets, and galaxies trace back to those early irregularities. Without them, space would have remained an even, featureless gas. Nothing complex would form. Clear evidence for this smooth beginning comes from a faint glow that still fills the sky in every direction. It is called the Cosmic Microwave Background, or CMB. Two radio astronomers, Arno Penzias and Robert Wilson, detected it by accident in the 1,960 seconds while working with a large microwave antenna. The CMB is the cooled remnant of the first light, able to move freely through space. At about 380,000 years after the Big Bang, the universe had cooled enough for simple atoms to form. Once atoms formed, light was no longer scattered at every step, and it began a long journey. As space kept expanding, the light stretched into microwave wavelengths. Today it arrives as a near uniform background. When scientists mapped the CMB with high precision, they found it was not perfectly uniform. There were spots just a bit warmer and just a bit cooler than average. Those temperature differences reflect small changes in density. They are the same faint wrinkles from the early universe. Preserved in light, gravity later used them as a guide. Denser patches pulled in more matter. Less dense patches slowly emptied. The CMB is therefore a snapshot of the universe. As a newborn, it shows a glowing fog with subtle variations that carry the first blueprint of structure. Why was the universe so smooth to begin with? The best explanation is inflation. Inflation refers to a very rapid expansion in the tiniest fraction of a second after the Big Bang. Space itself stretched far faster than the speed of light can move through it, which is allowed because it is space expanding, not objects moving through space. This fast expansion evened out irregularities across large distances. At the same time, quantum effects were at work on the smallest scales. Energy at tiny scales is never perfectly stable. It fluctuates. Inflation magnified those fluctuations, turning them into the small density ripples seen in the CMB. In short, the universe became smooth when viewed at large scales and slightly wrinkled when viewed up close. Those small wrinkles became the scaffolding on which later structure formed. For the first few 100 million years, the universe stayed calm. There were no stars yet, no bright galaxies. Hydrogen and helium gas filled space like a thin, even fog. If you could drift through it, you would see a dim glow, slowly reddening and fading as expansion continued. This period is often called the Cosmic Dark Ages. The main action during this time was quiet and invisible to the eye. Gravity gently pulled on the slightly denser regions, making them denser still. Regions with less matter became emptier. The stage was set for the first lights to turn on, but not yet. The balance in those early conditions was delicate. With no tiny variations at all, gravity would have had nothing to amplify. Structure would never have formed. With variations that were too large, matter might have collapsed too quickly into black holes, leaving little room for orderly growth. Reality fell between those extremes. That precise balance made it possible for galaxies and stars to appear and, much later, for life to arise on at least one small planet. The CMB is sometimes called the universe's baby picture because it preserves that balance in simple form. At first glance, it is a gentle pattern. Hidden in that pattern is a plan for how matter would arrange itself over time. The early stages are calmer than the word bang suggests. After the first fractions of a second, the broad view is not chaos, but a largely uniform expansion. Gravity's slow work begins on top of that smooth background. The cosmic web was already implied by the first ripples, though not yet visible. The information was present, like ink that would appear only when later processes developed. A simple way to describe those first moments is as a slow release rather than a violent burst, a steady filling of space with matter and light, almost perfectly balanced. From that calm start, gravity would draw threads, weave filaments, and carve out large structures. In the early quiet, The universe waited while time did its work. Beneath that smooth appearance was a kind of restlessness. On scales far smaller than atoms, nature does not sit still. Fields and particles show constant small activity. This is called quantum fluctuation. Even an ideal vacuum is not truly empty. Energy changes by tiny amounts, and pairs of particles can appear and disappear within very short times. During inflation, those microscopic jitters were stretched to much larger scales. They left faint marks in the density of matter and in the CMB. A clear picture helps. Think of a calm pond. From a distance, the surface looks still. Look closely, and you notice fine ripples. Now imagine the pond itself expanding very quickly. Those small ripples would be spread out into larger patterns. That is like what inflation did to quantum fluctuations. It took tiny variations and imprinted them on the fabric of space. The result was a map of slight highs and lows in density. Some places had a little more matter than average. Some had a little less. The size of the difference was extremely small, about 1 part in 100,000, but that was enough. Over billions of years, gravity amplified the higher parts and drained the lower parts. From such fragile beginnings, the large-scale structure took shape. It is striking that so much of what we see can be traced back to this small-scale behavior. The Milky Way, with its hundreds of billions of stars, the sun shining steadily, and Earth with its land, water, and living things all connect to those early variations. The universe can appear stranger than common sense expects, yet the data point in this direction, maps of the CMB made by missions such as the Planck satellite, show the pattern clearly. They display warmer and cooler spots across the sky. The warmer spots mark slightly denser regions. The cooler spots mark slightly less dense regions. Turning such a map in your hands is like looking at a weather chart for the young universe. Instead of storms and clear skies, the chart points to where galaxies and empty regions would later grow. The fine balance of these early fluctuations matters. If the variations had been much larger, early collapse would have dominated, and stable structures like galaxies might have been rare. If they had been much smaller, gravity would not have had enough of a head start to build anything significant before expansion spread matter too thin. The real universe sits between those outcomes. It carries just enough imperfection to build complexity. Quantum ripples differ from the ripples we know from daily life in an important way. Ripples on water usually come from an outside push, a stone, wind, or a passing boat. Quantum fluctuations are intrinsic. They arise from the uncertainty principle, which says that certain pairs of properties, like position and momentum, cannot both be known exactly at the same time. That limit makes empty space active rather than static. In the very early universe, when it was smaller than a proton, these fluctuations happened constantly, bubbling and fading. Inflation then stretched and froze them on large scales. What began as tiny behavior became part of the universe's long-term plan. Another useful picture comes from baking. Dough starts smooth, but small air bubbles form inside at random. Let the dough rise, and those bubbles expand. Bake it, and you get the final structure of the loaf pockets and denser parts. On a vastly larger scale, the cosmic web shows a similar pattern. Voids resemble the open pockets. Filaments and clusters resemble the denser bread. What began as microscopic randomness eventually set the large-scale texture of the universe. It is tempting to treat those early fluctuations as trivial, but they are not. They explain why the night sky holds stars instead of remaining blank. They explain why matter gathered into galaxies, why planets formed in disks around young stars, and why life could arise on long-lived worlds. Without the restless uncertainty described by quantum mechanics, the universe might have stayed smooth and lifeless. Every clear night is quiet evidence that order can grow from very small, random beginnings. Scientists can measure how those first ripples still guide the present-day sky. Three-dimensional surveys map the positions of millions of galaxies across billions of light-years. The result is not a random spray. It shows clusters, long walls, and wide gaps that match the statistical scales predicted from quantum fluctuations stretched by inflation. What began as tiny bumps in fields we cannot see has been checked across vast distances as the pattern that matter followed while it settled and grew. There is a simple lesson about scale. The grandest structures we know, walls of galaxies extending for hundreds of millions of light-years, grew from the smallest uncertainties allowed by physics. The faint shiver of quantum fields became the skeleton that supports the universe. Stars can look fixed and eternal, yet their very existence depends on a modest fact. The early universe was not perfect. It was not a flawless canvas. It carried faint streaks of higher and lower density. With time, those streaks became rivers of matter. Galaxies formed like bright beads along those ancient lines. Every light above us is, in its own way, a memory of the universe's restless beginning. That foundation may sound fragile, but it was enough. Enough for gravity to start its patient work. Enough to turn quiet variations into structure. Enough to give the cosmos a framework it would spend billions of years filling in. From quantum jitter to galaxies, the story begins with small wrinkles whose steady imprint is still written across the sky. When we describe the shape of the universe, it is easy to think that what we see is the whole story. Stars that twinkle, spiral arms that turn, and faint nebulae against the dark. Those sights are the garnish on a much larger dish. The deeper architecture is set by something that does not shine or absorb light at all. This unseen component is called dark matter. Without it, the cosmic web would never have taken shape. The idea sounds exotic, but the reasoning is straightforward. In the 1,930 seconds, Fritz Zwicky studied the Coma cluster and found that its galaxies were moving around the cluster's center far too fast. If only the visible matter were present, gravity would be too weak to hold the cluster together. It should have flown apart, yet it did not. Zwicky proposed that extra, unseen mass was providing the missing gravitational glue. He called it dunkel materia, or dark matter. Decades later, astronomer Vera Rubin measured how stars orbit within spiral galaxies. She expected the outer stars to move more slowly than inner ones, as planets do in the solar system. Instead, the rotation curves were flat. Far-out stars moved just as fast as the inner stars, as if each galaxy were wrapped in a vast, unseen halo of additional mass. The simplest explanation was the same matter we could not see was dominating the gravity. Multiple lines of evidence now point to that conclusion. About 85% of all matter in the universe is dark matter. Ordinary matter, the atoms that make up stars, planets, oceans, and people, is only a small share. The glowing part is the tip of an iceberg. The true bulk lies below the surface. What exactly is dark matter? That remains open. It does not emit, reflect, or absorb light. It does not interact strongly with normal matter in familiar ways. If a jar could be filled with it, the contents would pass through the jar, the table, and even the floor, drifting toward Earth's center, while almost never hitting anything directly. Yet dark matter interacts very strongly with one thing: gravity. That pull is what sculpts the web of the universe. A picture helps. When building a city, the first thing laid down is the network of roads, intersections, and highways. Later, buildings, homes, and parks gather along that network. In the same way, dark matter provided the framework for the cosmic web. Its filaments stretched across the early universe and set the routes along which ordinary matter could flow. Gas traveled along those threads and pooled in the densest knots. In those knots, stars ignited and galaxies assembled. Without the hidden scaffold, gas would have remained too evenly spread out for anything as large as a galaxy to form. We can see the effects of this invisible substance by studying how it bends light. General relativity says that mass curves space-time, and light follows those curves. When light from a distant galaxy passes near a large clump of dark matter, the image is distorted, magnified, or stretched into arcs. This gravitational lensing is a fingerprint of dark matter. By mapping those distortions across the sky, astronomers can trace the otherwise invisible web. The maps reveal filaments and halos of unseen matter crossing the universe, with bright galaxies hanging from them like dewdrops along a thread. The cosmic microwave background offers another test. Tiny temperature variations in that ancient light encode the density of matter in the early universe. When physicists compute the pattern using only ordinary matter, the result does not match what we observe. Include dark matter, and the pattern lines up. The early ripples demanded a hidden mass to grow into the web we see. Computer simulations make the case vivid. Feed the laws of physics into a supercomputer, set starting conditions based on early universe measurements, and let the model run. When dark matter is included, the result is a striking cosmic web. Filaments, voids, and clusters, much like the maps from real surveys. Run the same simulation without dark matter, and the result is underwhelming. The universe stays too smooth. Few major threads form. Reality seems to insist that dark matter is the quiet architect. Even so, the exact identity of dark matter remains elusive. Many scientists focus on exotic particles, weakly interacting massive particles, often called WIMPs or axions, very light particles that may have formed soon after the Big Bang. Experiments buried deep underground to block background noise, lofted by balloons into the upper atmosphere, and placed on satellites have searched for rare interactions or decay signals. So far, no direct detection has been confirmed. For now, dark matter plays a careful game of hide and seek. It avoids our detectors while leaving consistent, testable marks through gravity. The fact that most of the matter in the cosmos is invisible may feel unsettling, but it adds depth rather than taking it away. If everything were obvious to the eye, there would be little left to learn. Hidden layers make the world richer. Dark matter is not a minor footnote. It is central to how the universe works. When we watch stars, we are watching actors perform on a stage built and shaped by an unseen crew. Dark matter sets the stage, lays out the routes, and guides the action. The luminous parts follow a choreography written by an invisible partner. The cosmos is not only bright, it is scaffolded by something we do not see. Gravity ties this picture together. We often imagine gravity in dramatic scenes, apples falling, moons circling, but in the early universe it worked with patience. It did not fling matter into place with sudden bursts. It acted like a careful sculptor, tugging gently on the small ripples left by inflation and set by dark matter's framework. Over very long times, those faint pulls grew, coaxing gas and particles into filaments that would one day stretch across the cosmos. At first, The universe held a nearly uniform fog of hydrogen and helium. No stars shone, no galaxies turned. Yet beneath that smooth surface were slight differences in density. Where the density was a little higher, gravity had a little more to work with. Those regions became gravitational traps that pulled in more gas and more particles, the way small rivulets gather raindrops and grow into streams. They became the foundations of structure. What stands out about gravity's role is how universal it is. Every particle exerts a pull, no matter how small. A single proton's gravity is unimaginably weak, but multiplied by numbers beyond counting, the effect becomes profound. Gravity has no off switch. It is always on, always reaching. Even across billions of light years, its influence stretches through space like an invisible net. As the slight overdensities grew, they began to lengthen into patterns. Matter did not collapse the same way in every direction. It collapsed anisotropically, unevenly, with different rates along different axes. This is where the large-scale shape emerges. If gravity had pulled equally from all directions, space might have ended up filled with isolated, nearly spherical clumps. But because of the dark matter scaffold and the small, directional differences in the early density field, collapse became easier along one direction than another. Matter first gathered into wide, sheet-like structures, then funneled into elongated filaments, like dough rolled into strands. Those strands became the highways of the cosmic web. Computer experiments let us watch this unfold step by step. Start with an almost uniform distribution of matter. Add the small early ripples measured in the cosmic microwave background. Let gravity do the rest. Matter does not fall straight inward. It streams along the invisible gradients set by the underlying mass. Dense regions pull material from far around them, but the flow has direction. Over time, matter slides into sheets, then threads, then nodes at the intersections. The pattern looks like veins in a leaf or channels in a watershed, not as decoration, but as a clear way to picture how flows prefer certain paths. Nature repeats useful shapes, and here, gravity is the artist that draws them at the largest scale we know. On human timescales, this work is too slow to see. A galaxy cluster does not grow like a flower opening overnight. It takes billions of years for gravity to pull matter into position. Think of a glacier that looks still yet carves valleys and shapes mountains over ages. Gravity is slower still, but its reach is larger. Given time, it rearranges the contents of the observable universe. The web that spans billions of light years was drawn not with speed, but with persistence. The elegance of the process is the way gravity amplifies small differences. A region that is just slightly denser than its surroundings pulls a bit more strongly. That extra pull brings in more matter, which makes it denser still, which strengthens its pull again. The loop reinforces itself until long filaments take form. Meanwhile, regions with slightly less matter lose even more as their contents drain away toward denser areas, leaving behind enormous voids. The cosmic web grows from gravity's habit of taking the smallest imbalance and leaning on it, slowly, until patterns appear across unreachable distances. When astronomers map millions of galaxies in 3 dimensions, the points do not look like random sprinkles on a black page. They form strings, walls, and wide empty basins that match what careful simulations predict from gravity acting on tiny early ripples. The largest sheets we observe, stretching hundreds of millions of light years, are monuments to a force that rarely rushes. Think less of a hammer, more of water shaping rock. The web is not a sudden event, it is a long weaving. Filaments are pulled out of an almost uniform fog, the way strands of wool are drawn from a bundle, thin at first, then steadier, then strong enough to guide everything else that follows. Nothing about the force itself is exotic. It is the same gravity that holds your feet to the ground and keeps the moon moving around Earth. The difference is only scale and patience. With that in mind, the night sky changes color in our thoughts. Each galaxy is not just drifting alone. It rides a thread. It is a bright bead on a line that runs for unimaginable distances. Those lines are not guesses. They were traced by gravity long ago, setting up highways that matter would follow. Our own Milky Way, with its hundreds of billions of stars, found its home this way. We live on a filament. The route was drawn long before our planet formed. A small change in gravity's strength, and the picture would break. If gravity were weaker, early ripples would have stayed small, never growing into filaments, clusters, and walls. If gravity were stronger, the pattern would have collapsed too quickly, turning much of the matter into black holes and leaving little room for galaxies to form and breathe. The web lives in a narrow middle ground. Gravity is strong enough to gather matter and gentle enough to let it evolve, merge, and settle into long-lived systems. In that sense, gravity behaves less like a ruler giving orders and more like a patient gardener. It does not impose shape by force. It coaxes it out, season after season. The trellis underneath is dark matter. The vines that climb are gas and stars. The result is the quiet order we see when we zoom out far enough. Step back far enough, and the beauty of the process is hard to miss. From a near featureless beginning, gravity spun lacework. From randomness, it raised geometry. The web shows that the universe is not fixed. It is active, always being shaped by pulls we cannot see with our eyes, across spaces and times that do not fit human instinct. The lesson is humble and clear. Large things can arise without violence. They can grow from steady, gentle work done over long periods. The filaments that cross billions of light years are proofs of persistence. Where threads meet, the picture changes. Intersections become luminous knots nodes, where gravity has pulled matter into deep wells. Inside these hubs, galaxies are gathered by the thousands. Stars are born in great numbers. The pace of change is high. A simple road image helps. Filaments are the long highways, and the nodes are the cities where those roads converge. Gas and galaxies travel along the highways and arrive at the hubs, where gravity binds them. In these places, the universe feels busy and loud in a way that empty regions do not. The scale is hard to hold in mind. A single galaxy cluster, the basic unit of a node, can contain hundreds to several thousands of galaxies. Each galaxy can hold billions of stars. Surrounding them is an unseen halo of dark matter and a deep pool of gas heated to tens of millions of degrees hot enough to glow in X-rays. Clusters are the most massive bound structures the universe makes. Their total masses reach into the quadrillions of suns. A well-known example is the Coma Cluster, a dense city of galaxies studied for nearly a century. The view is not a random swarm, it is a family bound together by gravity's steady hold. Every galaxy is moving fast, yet stays within the cluster's grip, circling the shared center of mass like bees around a hive. At the center of many clusters, a giant elliptical galaxy sits like an anchor. These titans grow through repeated mergers. Smaller galaxies stream in along filaments, collide, and combine. Over time, the central galaxy becomes bloated and bright. It is not a throne in any proud sense. It is a sign of long, quiet additions piled up over billions of years. The highways feeding the hubs matter just as much as the hubs themselves. Filaments deliver gas and galaxies, keeping the clusters supplied. Without that inflow, clusters would thin out. The web is not a frozen sculpture. Material continues to stream in. Astronomers call the ongoing flow accretion. As matter slides along the threads, clusters gain mass, galaxies collide more often, and new bursts of star formation light up the scene. In close quarters, galaxies tug one another out of shape. Some lose their gas to the thin, hot medium that fills a cluster. Some merge. Some are stripped into thin streams of stars that arc around the cluster center. Life near the hub is crowded and competitive. Farther out, along quiet filaments, galaxies evolve with less interruption. These hubs do not stand alone. Clusters often collect into larger associations called superclusters regions, where several clusters are connected by filaments over great distances. Our local address sits within the Virgo supercluster, which spans more than 100 million light-years and includes the Virgo cluster along with many smaller groups, including our own. Zoom out again and you find that even this is one part of a larger basin known as Laniakea, a giant supercluster complex 500 million light-years across. It gathers hundreds of thousands of galaxies into a gentle gravitational flow. In that city of cities, the Milky Way is one small light on a quiet street. The nodes tell another story as well. Growth comes in steps. Small structures form first and then assemble into larger ones. Tiny early ripples grew into small galaxies. Small galaxies gathered into groups and then into clusters. Clusters connected into superclusters, which together stitch the web. It is a nested, tiered cosmos. Each level sits on the scaffolding of dark matter and the long patience of gravity. Astronomers map these junctions with increasing care, using several tools: redshift surveys to place galaxies in 3 dimensions, X-ray observations to reveal hot gas in clusters, and gravitational lensing to trace dark matter by the way it distorts the images of more distant sources. The resulting maps are not random splashes. They are networks of bright nodes linked by pale strands. The pictures often look familiar. Put a map of the cosmic web next to an image of a neural network in a brain scan, and the resemblance invites comment. One is made of stars and gas, the other of cells and signals. The physics and biology are unrelated, yet both are natural systems that grew under simple rules that favor connection. The likeness is a reminder to be cautious and also to be curious. Patterns reappear in nature for reasons worth understanding. At the same time, the web faces pressure from the general expansion of the universe. A push we call dark energy drives that expansion and works against clustering. For now, clusters and nodes remain intact. They are anchors in a sea that is slowly stretching. Far in the future, their supply lines may thin as expansion continues to speed up. In the present, they are busy downtowns in an otherwise quiet land. From Earth, with the naked eye, the sky can feel like a scattering of isolated islands. Nodes teach a different lesson. Galaxies live in neighborhoods. They meet at crossings. They are tied to a system bigger than any single object. Our own galaxy is part of this web of connections, joined by filaments to other groups and drawn, with many neighbors, toward more massive hubs. The web is gravity's social instinct at scale. Matter tends to gather. It prefers company. It builds hubs where activity peaks and then spills outward along the roads that led in. Most of this structure remains invisible. The galaxies are like streetlights in a night city. They outline the routes, but the true mass the dark matter stays unlit. We infer it from motion, from lensing, from background light. Its presence is not guesswork. It leaves marks we can measure. Those marks show a network that holds galaxies in place, stitches them into clusters, and ties the wider pattern together. To drift through a node would be to see the universe at its most energetic. Collisions, arcs of stripped stars, shocks in hot gas, and long inbound flows all share the same space. It is a crossroads written in gravity. If nodes and filaments are highways and cities, the voids are deserts, vast regions where galaxies are few and darkness is deep. Emptiness may not sound like a story, but the contrast is essential. Without the empty, there is nothing to outline the full. Voids are large. Typical ones span tens of millions of light years, and the biggest reach more than 100 million. Imagine a sphere so big that, if the Milky Way sat at its center, every galaxy visible to the naked eye would fit inside with room to spare, and the sphere would still look quiet. These are places where gravity has drawn matter away, down the slopes towards surrounding filaments and nodes, leaving behind hollows in the landscape. Early three-dimensional maps from the 1,970 seconds and 1,980 seconds delivered a surprise. Astronomers expected a fairly even spread, with some clumps. Instead, they found dramatic patterns, long chains and walls surrounding enormous empty spaces. The voids were not small gaps. They dominated the view. The web is as much about hollows as it is about bright lines. A striking case is the Botez void, found in 1981, a region roughly 330 million light-years across, with only a handful of galaxies known inside it. That diameter is thousands of times the width of the Milky Way. To travel through it would be to spend hundreds of millions of years crossing mostly darkness, meeting only the rare solitary system. Voids are not perfect vacuums. They hold dark matter, thin traces of hydrogen gas, and occasional galaxies. Their density is low, around 1/10 of the cosmic average. That difference matters. Gas there is often too thin to cool and collapse into stars at the usual pace, so the regions stay faint. Think of them as backwaters bypassed by the strong flows. Galaxies that do live in voids tend to be unusual. With few neighbors to disturb them, they evolve slowly and keep their gas longer. Some are small and irregular, forming stars at an easy rate. Some are isolated spirals, slowly turning with wide, undisturbed disks. Studying them is hard because they are far apart and faint, but the reward is real. The comparison between busy hubs and quiet voids shows how environment shapes a galaxy's life. Voids also help with one of the hardest questions in cosmology, the nature of dark energy, the driver of cosmic expansion. Because voids are underdense, they expand faster than the average. That faster flow exaggerates the signal we want to measure. By mapping how galaxies sit within and around voids, and by tracking how voids grow and move over time, astronomers can sharpen their estimates of how strong dark energy is and how it changes the universe's growth. The emptiest places can tell us the most about the long-term future. In simple terms, voids act like responsive parts of a stretching fabric. Watch them carefully, and you can learn how the fabric itself is being pulled. Voids change how we picture the universe. Without them, space would look like a crowded wall of galaxies with no room to breathe. Instead, the pattern feels balanced fullness next to emptiness, light beside dark, structure outlined by silence. The contrast makes the web stand out. threads of matter are clear precisely because hollows surround them, like foam with bubbles or lace with open spaces. The pattern is defined as much by its gaps as by its strands. To drift through a true void would be to meet deep stillness. There would be no nearby cities of stars, no bright clusters buzzing with action, only a faint background glow that fills all of space. The nearest big galaxy might sit hundreds of millions of light years away, yet gravity would still be quietly at work. Over long times, matter continues to slide out of the empty region toward the filaments around it. The void becomes even more underdense. It is not a frozen hole. It is a slow flow that deepens with time. Voids also affect how galaxies move along their edges. Clusters pull things inward. Voids do the opposite in practice. Not because they push with a special force, but because the pull from the denser regions outside is stronger than the pull from the thin interior. The result is a net motion away from the emptiness. In this sense, voids help shape large-scale flows. They are silent shapers, guiding traffic without ever lighting up. It is hard to grasp how large these hollows are. When we call them empty, we mean they hold much less matter than average, not that they are perfect vacuums. A better picture is a faded watercolor where most of the paint has lifted. There is still some color left, dark matter, thin threads of hydrogen, a few lonely galaxies, but not much. For some people, so much near nothing feels unsettling. For others, it is calming. The emptiness gives the web room to breathe. Even at the largest scales, the universe keeps wide stretches of quiet. The story of voids is about balance. The bright gathers make sense only next to the open spaces. Filaments and nodes gather attention because the hollows frame them. They are the rests that let the music be heard. The web is a network of matter, but also a pattern of presence and absence woven together. Turning such a vast picture into an actual map is not simple. Space offers no signposts. The web does not hang labels on its roads or borders. Filaments and nodes are invisible to the eye and are written in gravity rather than light. Yet astronomers have learned to chart them. They have built a set of tools to turn the sky into a usable atlas and to reveal the skeleton beneath the stars. Their first obstacle is basic: distance. A telescope gives a position on the dome of the sky, up near one constellation, down near another. That is 2 dimensions. To find the web, you need depth. Without distance, the view is a flat painting, pretty, but misleading. The key to depth is redshift. Because the universe is expanding, light traveling through it gets stretched. Longer wavelengths are redder. The farther the light has traveled, the more it is shifted toward the red. By measuring that shift carefully in a galaxy's spectrum, astronomers infer how far away it lies. It is like the way a siren's pitch drops as an ambulance moves away, except the effect stretches over millions or billions of years, and the siren is starlight recorded by a spectrograph. With redshifts in hand, researchers began to place galaxies in 3 dimensions. What once looked like a random sprinkle turned into ordered structure. Galaxies outlined long strings and tall walls and left great empty regions between them. The web stepped from theory into view. Early efforts were small by today's standards, yet powerful. In the 1,970 seconds, the CFA Redshift Survey started to plot galaxies with depth. As data grew, the picture sharpened. The universe had texture. The first slices looked like branching coral and empty bubbles. These were the first clear glimpses of an underlying network. As instruments improved, the maps expanded. The The Sloan Digital Sky Survey, SDSS, which began in the late 1992s, marked a turning point. A dedicated 2.5-meter telescope at Apache Point in New Mexico scanned wide areas of sky, measuring spectra for huge numbers of objects. Instead of staring deeply at one small patch, SDSS swept across large regions, collecting redshifts by the hundred and then by the million. The results were turned into a three-dimensional atlas. When visualized, the map showed filaments that ran for hundreds of millions of light years, knots where clusters gathered, and large voids in between. For the first time, the web could be seen as mapped reality, not just an idea. These maps were more than images. They were tests of physics. The way galaxies cluster on different scales checks ideas about dark matter, dark energy, and how structure grows. In the pattern, scientists see a subtle signal called baryon acoustic oscillations, faint relics of sound waves that traveled through the hot plasma of the early universe. BAO act like a standard ruler built into the map. By measuring this ruler at different distances, cosmologists can track how expansion has changed with time, which in turn informs models of dark energy. A galaxy map is therefore not only a chart of where things are, but also a record of how the universe grew. Redshift surveys are one tool. Others look at different pieces of the puzzle. Gravitational lensing measures how mass, especially dark matter, bends the paths of light. By studying how distant galaxy images appear slightly stretched or skewed across the sky, astronomers infer where the unseen mass lies. In effect, they draw a mass map instead of a light map. It is like seeing wind by how trees sway. Another approach follows thin gas through absorption. Distant quasars shine like bright beacons. As their light passes through intergalactic hydrogen, it picks up a series of absorption lines. By sampling many quasars in different directions, astronomers reconstruct where the gas lies, the so-called Lyman alpha forest, thus tracing the filaments that connect galaxies. Each method adds a layer. One shows the roads for stars. One shows the dark scaffolding. One shows the faint gas between them. Put together, the invisible becomes visible. The scale of these atlases is hard to absorb. On Earth, cartography deals in kilometers and continents. Even the largest map wraps a world about 40,000 kilometers around. Cosmic cartography deals in millions of light years. A single filament can run for 500 million. A void can span 100 million. These are not maps of seas and land, but of patterns so large that they bend the mind. And yet, careful observation turns them into something our minds can hold, a network with features we can name and measure. There is also a certain elegance in how these maps look. Visualizations of the cosmic web are among the most striking images in astronomy. They show glowing networks that resemble lace, coral, or neural tissue. They are honest products of data and physics, not decoration. Still, the beauty is real. It is the beauty of a simple rule: gravity acting over time on small differences, drawing a clean pattern at a grand scale. The work continues. New instruments add depth and reach. The Dark Energy Spectroscopic Instrument, DESI, for example, is measuring redshifts for tens of millions of galaxies and quasars to build the largest three-dimensional map yet. Each new survey sharpens the web. Filaments become more defined, nodes more detailed, voids more clearly marked. We are still early in the project of mapping the universe's full skeleton. Better tools and longer baselines promise clearer tests of dark energy and better measures of how structure has grown. These charts are more than technical feats. They show human curiosity at its best, an attempt to make sense of distances so large that units like kilometers are useless. They remind us that patterns exist even when our first glance sees only dots. With patience and careful method, we find structure in the spray. The universe is not a chaotic scatter, but a woven layout. By layering methods and sharing data, we have learned to trace the threads. The SDSS story illustrates this well. At the turn of the millennium, the project set out to build the most detailed, three-dimensional map of the universe so far. It took the idea of star charts guides for ships crossing oceans and scaled it up to guide our thinking across cosmic distances. Instead of coastlines, the map would show galaxies and clusters. Instead of ports, it would show nodes at the crossings of filaments. The survey was funded in large part by the Alfred P. Sloan Foundation, and the telescope was engineered for wide-field work. Its detectors could record hundreds of spectra at once, letting the team measure distances for unprecedented numbers of targets. At first, the goal felt bold. Could one project really map a meaningful share of the sky in depth? As results arrived, the answer proved to be yes. Over the years, SDSS collected redshifts for millions of galaxies. The night sky shifted from a flat dome to a layered structure. One early visualization revealed a giant feature named the Sloan Great Wall, more than 1.5 billion light-years across. Even light, moving at about 300,000 kilometers per second, would need that many years to cross its length. It became one of the largest coherent structures known and a plain sign of the Webb's scale. Sloan's power was not only in size, but in precision. Good spectra placed each galaxy with care in 3 dimensions, showing not only where it was, but how it connected to neighbors. The Webb no longer needed to be inferred from hints. It was drawn directly in the data. Clusters shone as knots. Filaments ran between them. Great hollows opened in between. The survey also tightened checks on BAO and other measures of clustering, which in turn sharpened models of dark energy and matter. In practice, SDSS became a workhorse. Its public data supported countless projects, from mapping the Milky Way to cataloging quasars. Its open releases let students, amateurs, and experts alike explore the sky from their desks. Few telescopes have contributed to more studies. The survey also changed how we visualize the universe. When its data were plotted in wedges, fan-shaped slices reaching outward from Earth, each dot marked a galaxy. Together, the dots traced out coral-like branches, filaments and voids radiating in many directions. These images turned into icons in classrooms and planetariums. They made a clear point in a single glance. The universe is not a random spray of galaxies, but an organized, interconnected web. What makes the Sloan map especially powerful is how it gives us a place in the pattern. It is one thing to read that the Milky Way belongs to a small group, that our group sits on the outskirts of a larger cluster, and that the cluster is part of a wider supercluster inside an even greater web. It is another thing to see that address plotted. Our neighborhood becomes a small cloud of points connected to a longer thread that runs for hundreds of millions of light years. The map shows our path inside Laniakea, the supercluster that gathers the Virgo cluster, our local group, and many others into a gentle flow. Seeing that position turns an abstract idea into something concrete, a cosmic address traced along a filament that existed long before Earth formed. Sloan is not the last word. It is a snapshot, a careful first draft of cosmic cartography. Newer projects reach farther and show finer structure. The Dark Energy Spectroscopic Instrument, is measuring redshifts for tens of millions of galaxies and quasars, tightening the three-dimensional atlas. The European Space Agency's Euclid mission is mapping the sky in visible and infrared light, charting weak lensing distortions with high precision to reveal dark matter directly through its effects. These efforts add depth, fill gaps, and sharpen the scale of features first sketched by Sloan. Even so, Sloan remains a landmark. The survey that made the web visible in a way most people could understand at a glance. Dots arranged not as random gravel, but as lines, walls, and hollows. A visualization from Sloan looks simple and steady. Each dot is a galaxy, a city of stars, and many of those stars likely host planets. Plot enough dots and order emerges. Threads stretch across the frame. Knots mark clusters. Wide, empty basins show where matter is scarce. The feeling is not dramatic, but clear. The size humbles. The pattern reassures. The web may be invisible to the eye, yet surveys sketched its outline and revealed the support under the luminous scene. In that way, the map is more than a database. It is a record of careful measurement, consistent method, and patient reasoning. Light, for all its speed, is not entirely free. It can travel for billions of years, yet its path bends when it passes mass. That bending is one of general relativity's cleanest predictions and one of astronomy's most useful tools for uncovering the invisible skeleton of the cosmos. By measuring how light curves around massive structures, scientists can map dark matter and trace the hidden threads that hold the web together. The method is called gravitational lensing, gravity's signature written on light. A simple picture helps. Hold a magnifying glass over a page, and the letters shift as the glass redirects the rays. In space, mass plays the role of the glass. A galaxy, a cluster, or even a long filament of dark matter warps space-time, curving the path of passing light. To us, a background galaxy can look stretched, magnified, or even doubled and tripled. The effect is like a funhouse mirror, except the mirror is the geometry of space itself. Classical physics did not expect this. Newton's gravity explains orbits, but does not bend light. In 1915, Einstein reframed gravity as the curvature of space-time. Objects, including light, follow the curves. A clear test arrived in 1919. During the total solar eclipse, astronomers measured star positions near the darkened sun and found the starlight bent by exactly the amount Einstein had predicted. Lensing moved from idea to measurement, and with time it became a core tool for weighing the unseen. Lensing comes in two main forms. Strong lensing appears when a very massive object, often a galaxy cluster, sits nearly in line with a more distant source. The foreground mass distorts the background light so strongly that it makes arcs, multiple images, or even complete rings known as Einstein rings. These shapes are bright signs that a deep mass well lies in the way. Weak lensing is subtler. The distortions are too small to notice in any single galaxy. But by averaging the shapes of millions of background galaxies across a wide field, astronomers detect a statistical stretch that reveals where mass, especially dark matter, sits along the line of sight. It is like watching a forest in a breeze. A single leaf tells little, but thousands leaning the same way show the wind. Using these approaches, teams have drawn maps of dark matter that match what simulations predict. Images from the Hubble Space Telescope, for example, reveal dark filaments linking clusters. The faint pattern in galaxy shapes turns into a clear picture of mass bridges that do not shine. The agreement is important. models that begin with tiny early ripples and include dark matter produce lensing patterns that look like the ones we observe. It is as if a room written in invisible ink was suddenly lit, and the hidden lines became readable. Some cases are especially vivid. Abell 1689, a massive cluster more than 2 billion light-years away, produces dozens of long arcs wrapped around its center. Each arc is the stretched image of a much more distant galaxy, diverted by the cluster's gravity. By modeling the positions and curves of these arcs, astronomers reconstruct how mass is distributed within the cluster. The luminous galaxies and the hot gas that shines in X-rays account for only part of the total. Most of the mass lies in a broad, unseen halo of dark matter that the light traces as it bends. Another famous test is the bullet cluster, formed by two clusters that collided. As they passed through each other, the hot gas cloud's ordinary matter slammed together and slowed, glowing brightly in X-rays. The galaxies, being far apart from one another, mostly passed through. Lensing maps show that the bulk of the mass moved with the galaxies, not with the slowed gas. That separation is hard to explain without dark matter. Nature, in a sense, ran an experiment. It split ordinary matter from the mass that carries most of the gravity, and the lensing revealed the split. On larger scales, weak lensing surveys chart dark matter across wide regions of sky. The Dark Energy Survey and Japan's Hyper-Suprime-Cam survey have traced a network of dark filaments threading between clusters over billions of light-years. Each tiny skew in a background galaxy adds a bit of information. Stack enough of those clues, and a skeleton appears. These maps test cosmological models by comparing the observed web to simulated ones and help measure how quickly structure grows key data for understanding dark energy's effect on the expansion of the universe. Lensing does more than weigh the web. It also acts as a natural telescope. Strong lensing boosts the light from faint, distant galaxies, making visible systems that formed only a few 100 million years after the Big Bang. In that way, the universe supplies its own zoom lenses. We study the first galaxies, not because we built impossible optics, but because gravity lined up sources and lenses in our favor. Part of lensing's elegance is its directness. Once curved space-time is accepted, light travels for eons, then skims past a mass at the right angle and distance. The path bends, like a runner leaning into a turn. When the light reaches our telescopes, the image is warped. The warp is information. By decoding the pattern, scientists reconstruct the invisible structures along the way. We infer long, unseen filaments, not by touching them, but by noticing how they tilt the images of galaxies billions of light-years behind them. It is a quiet method, yet precise gravity leaves fingerprints, and light records them. In that sense, gravitational lensing is the universe cooperating with our questions. Space and time, shaped by mass, become instruments. Through these curved paths of light, the hidden architecture is drawn into view, and the threads of the web are traced across the sky. Galaxies are not scattered like sugar across a counter. They gather along interconnected filaments, strung like beads on lines we cannot see directly. These filaments are the highways of the cosmic web, and galaxies follow them. They cluster where strands cross and thin out toward the great voids. To understand why, look at how matter flows and how the web acts as a delivery system that guides material to the places where galaxies can form and grow. The base of this pattern is gravity working on dark matter. Long before the first stars, the universe held an invisible network of dark matter filaments. Those filaments carved channels down which gas could slide. Hydrogen and helium, the simple elements forged in the Big Bang, did not spread evenly. They fell along gravitational slopes laid out by dark matter. As rain runs into rivulets and then into streams and rivers, gas collected along the threads. The result was a kind of plumbing. Filaments became supply lines, carrying raw material to growing structures. Along those lines, gas cooled and condensed into dense clouds. In the densest spots, stars turned on. Where multiple filaments crossed, flows brought even more material, and clusters took form. In this way, the web served as both blueprint and builder. It set the sights for galaxies and provided the fuel. Without the guidance of filaments, matter might have stayed too thinly spread to reach the densities needed to ignite stars. Computer simulations make this process vivid. When models include dark matter and gas and start from the measured early ripples, filaments appear naturally. Gas moves along them like traffic on a multi-lane road, funneling toward hubs where clusters grow. In the simulations, galaxies almost never sit far from the threads. That picture matches what surveys show. Real galaxies overwhelmingly line up along filaments and rarely wander deep into voids. The few that do often look isolated and unusual, starved of fresh gas. Feeding also shapes behavior. Streams of cold gas can flow straight into a galaxy along a filament, sometimes triggering starbursts as new material arrives. The web can influence orientation as well. Spiral galaxies often align their spins with the direction of the filament they occupy, a sign that the flow of matter helps set how a disk turns. The web is not uniform. Some filaments are thick and busy, packed with gas and galaxies. Others are thin and faint. Thickness and density help set the kinds of galaxies that form. Heavy filaments tend to host larger systems and feed rich clusters, while slender strands support smaller, fragile ones. At the crossings, the process becomes dramatic. Clusters at filament junctions act like major interchanges where multiple streams converge. They are still being fed today. Galaxies move inward. Some collide and merge. Some are stripped of gas by the thin, hot medium that fills a cluster. Bursts of star formation flare and fade as supplies ebb and flow. The system is active, a steady exchange set by inflow and environment. The supply lines do not close, so the busiest hubs remain lively even now. This flow helps explain why star formation has not ended. The average rate of star birth peaked about 10 billion years ago and has declined since, but many galaxies still form stars because fresh gas keeps arriving along the web. Without resupply, disks would have run dry and faded. The web is more than scaffolding. It is nourishment, delivering fuel that keeps the lights of the cosmos on. Filaments also bring neighbors together. Gravity within the strands can draw galaxies into encounters. Mergers change shapes and build mass, turning two small systems into one larger one, and often igniting waves of new stars. In that way, the web does not only place galaxies, it directs their interactions. A quiet spiral, sliding along a thread may, after many orbits, meet a partner and merge an event set in motion long before by the flow of matter through the strand. Astronomers often borrow language from ecosystems to describe this. On Earth, rivers and valleys guide water and nutrients, shaping where life thrives. In space, the pattern is similar in spirit. The voids are deserts thin, wide, and spare, while the filaments are fertile river valleys. Along those valleys, gas flows, galaxies grow, and a rich variety of forms is sustained across time. The web is not alive in any literal way. Yet it acts like an environment. It sets the conditions that decide where galaxies can form, how they grow, and how they change over time. There is a clear, almost simple beauty in this arrangement. Galaxies with their stars, planets, and chances for life do not sit in space at random. They are linked by invisible highways of matter. On the largest scales, the universe is about connections. Each galaxy belongs to a wider network, filaments supplied with gas. Gravity keeps it tied to neighbors across hundreds of millions of light years. When we study the web in simulations, or read it from surveys, we see gravity and dark matter at work together. The filaments are not just lines on a chart. They are the arteries of the cosmos, carrying material into galaxies and clusters and keeping the lights of the universe on. Every star you can point to was likely made possible by one of these hidden supply lines. Every galaxy is a traveler moving along them. These threads are both pathways and lifelines. They explain why galaxies appear where they do, why clusters sit at crossings, and why the universe has clear structure instead of formless fog. They act like couriers, delivering gas and dark matter along routes that are not visible to our eyes but are traced by physics. In this quiet way, the web weaves galaxies into place. The bright systems that dot the sky are the visible parts of a framework shaped by an unseen skeleton. Step up in scale, and the pattern continues. The universe is not only a collection of galaxies, or even of clusters. It is stitched into larger shapes that span hundreds of millions of light years. These are superclusters and walls, the biggest coherent features we know, tied together by gravity and outlined by filaments. Looking at them shows how large the cosmos really is and how modest our own Milky Way is by comparison. Our local supercluster is called Laniakea, a Hawaiian word that means immense heaven. The name fits. Laniakea stretches roughly 500 million light-years and includes more than 100,000 galaxies. Among them, the Milky Way. Many filaments meet inside this region, and their flows point toward a deep gravitational basin, often called the Great Attractor. That concentration of mass tugs on galaxies from far away, guiding their motions over very long times. The scale is hard to grasp. Crossing Laniakea at the speed of light would still take about 500 million years. For reference, Earth's full history from its formation to now spans about 4.5 billion years. You would need to traverse Laniakea nearly 10 times to match that age, and Laniakea is just one piece of a much larger pattern. Astronomers outlined Laniakea by tracking the motions of thousands of galaxies. They saw that the motions were not random. They flowed like rivers toward a basin. That flow marked the supercluster's extent and showed that the local group, the Virgo cluster, and many other groups all belong to one larger domain. In other words, our neighborhood is part of a broad current set by gravity. We are strands in that current, moving together toward a region we still cannot view in full detail. Elsewhere, other superclusters show the range of this architecture. The Shapley supercluster, about 650 million light-years away, is one of the most massive concentrations of galaxies nearby. It holds thousands of galaxies in many clusters, and its gravity influences not only its own members, but also our motion by a small amount. In a simple image, Shapley is like a heavyweight node in the network, adding a steady pull to the general flow. Then there are the walls, truly immense alignments that sweep across the maps like ridges. A famous example is the Sloan Great Wall, revealed in early slices from the Sloan Digital Sky Survey. It runs for more than 1.5 billion light-years, made of chains of clusters and superclusters. Seen from the outside, such a wall would look like a vast, glowing sheet with filaments branching away. Structures like these test our sense of scale. A single galaxy already contains billions of stars. A cluster holds hundreds to thousands of galaxies. A wall extends orders of magnitude beyond that. They are like continents on the universe's map, with filaments as their mountain ranges and voids as their seas. What makes these features especially interesting is how well they match theory. Their sizes and shapes line up with models that include dark matter and dark energy, and start from the tiny early ripples we see in the cosmic microwave background. Under gravity's steady pull, those small differences grow into superclusters and walls. The design is not accidental. It is the natural outcome of simple rules applied over long times. There is debate at the edges. Some ask whether a structure as large as the Sloan Great Wall is an object in a strict sense, or whether its size strains the idea that the universe becomes uniform if you zoom out far enough. These questions keep observations and models honest. At the same time, dark energy adds another twist. Because it speeds up the expansion of space, it will slowly reduce the growth of the largest bound structures. Far in the future, some connections that are still forming now will fade. For the present, though, superclusters and walls stand as records of gravity's patient work. When we place the Milky Way into this layout, the scale becomes personal. Our spiral, with its hundreds of billions of stars, is a small swirl inside Laniakea. Laniakea itself is only one region among many, with giants like Shapley elsewhere in the map, and other walls extending beyond the part of the universe we have charted. The web stretches farther than we can currently observe, and each new survey extends our view. The names we give, immense heaven, great wall, attractor, reflect both the size and the structure. They remind us that the universe is not chaos, but organized growth. To make this layout useful, it helps to write down an address. On Earth, an address lists a street, a city, and a country. Zoom out, and a deeper address emerges. You live in a solar system. That system orbits inside a galaxy. The galaxy belongs to a small group. That group sits near a cluster. The cluster is part of a supercluster, and the supercluster is tied by filaments into the larger web. Knowing where the Milky Way sits means placing us inside that full chain. Start with the solar system. The Sun and its planets orbit around the center of the Milky Way, which is a barred spiral about 100,000 light-years across, with perhaps 400 billion stars. Big as that is, it is only a local neighborhood on cosmic scales. The Milky Way belongs to the local group, a modest collection with more than 50 members. The Milky Way and the Andromeda Galaxy are the two largest. Triangulum is a smaller companion. Most of the rest are dwarf galaxies, faint, low-mass systems that orbit the larger ones. The local group spans roughly 10 million light-years, which is huge in human terms and small in the language of the web. The local group lies on the outskirts of the Virgo cluster, about 55 million light-years away, a rich cluster with more than 1,000 galaxies. Many of them are giant ellipticals built from mergers over time. Virgo acts like a downtown in the broader city of nearby galaxies. Smaller groups like ours are drawn toward it by gravity, even while we orbit within our own small suburb. For a while, Virgo seemed like the center of our larger environment. In 2014, a more complete view came into focus. By mapping galaxy motions in detail, researchers found that Virgo itself is part of a larger flow The name given to this larger basin is Laniakea, our true supercluster scale address. To define Laniakea, scientists looked at where galaxies are and how they move. Galaxies do not sit still. They drift under many gravitational pulls at once. By tracking those motions, the team found that the local group, Virgo, and many other collections all flow toward a region nicknamed the Great Attractor. That flow outlines Laniakea's boundary. The concept is simple: a set of galaxies that share a destination and thus belong to one basin of attraction. It is like learning that your town, city, and neighboring cities are part of one large watershed. The discovery expands how we think about home. Inside this basin, the Milky Way sits near the edge of a flattened arrangement known as the local sheet. The local sheet includes Andromeda, Triangulum, and many dwarf companions. The sheet is part of a larger complex of structures that feed into the filaments of Laniakea. Using an earthly picture, if the universe is a vast city, the Milky Way is not a landmark building. It is a modest home on a quiet street. From our perspective, it does not feel small. The band of the Milky Way is a bright river across the night. We orbit within one of the spiral arms, about 27,000 light-years from the center, far enough from the active core to be safe, close enough to see a rich sky. In practical terms, we live in a stable suburb. Now imagine zooming out. The solar system shrinks to a dot. The Milky Way shrinks to a point of light. The local group becomes a small cluster of points. The Virgo cluster appears as a dense patch. Pull back farther and the filaments of Laniakea come into view, stretching for 500 million light-years, with nodes at their crossings and voids between them. The Milky Way becomes one faint mark on one thread in this larger picture. The view can feel humbling, but it also helps. It shows that we are not floating in a featureless expanse. We sit in a structured neighborhood. These layers, galaxy to group, to cluster, to supercluster, to web, make a simple point about belonging. Our system is not isolated. It is connected in predictable ways. The links are set by gravity and the flow of matter along the web. Laniakea may not be the final outer boundary of our region. Beyond it are other superclusters, other flows, and other great features that we have not yet mapped in full detail. Our address may need updates as surveys improve. For now, Laniakea is a useful frame. It holds the Milky Way, the stars we see, and the local structures we measure. In this frame, the Milky Way is not adrift. It is part of a strand that ties us to galaxies far beyond what we can reach. All of them move together under common pulls. When you look up at the night sky, each star is a local light, but the view comes from a small street corner inside a very large city. The pattern is layered, and we are one layer within it. The address that matters most at this scale is not a street or a country. It is a place inside an immense web of galaxies, with gravity as the quiet link that holds the pattern together. Our home is not confined to Earth or even to the Milky Way. It is the web itself, the lattice of filaments and nodes that holds the universe together. That is our address, written across the stars. Yet the web, for all its reach, is not fixed in its current form. For billions of years, gravity working with dark matter has woven galaxies into threads and knots. All the while, another influence has tugged the opposite way. We call it dark energy. It drives the expansion of space and slowly pulls the web wider. Where gravity gathers, dark energy separates. The balance between the two has set the pace of cosmic history, and it will likely set the web's long-term fate. The idea of an expanding universe reaches back a century. In the 1922, Edwin Hubble showed that distant galaxies are moving away. Their light is shifted to longer, redder wavelengths, and the farther a galaxy is, the faster it appears to recede. For decades, many expected this expansion to slow as gravity worked to pull everything back. Some even asked whether the universe might someday reverse into a big crunch. That view changed in the late 1992. Two teams measured the brightness of very distant supernovae exploding stars used as standard candles and found the opposite trend. The expansion is speeding up. Some unknown pressure is pushing galaxies apart, faster and faster on the larger scales. We gave it a plain name that admits how little we know: dark energy. Dark energy is not like the matter and light we know. It does not clump, glow, or thin out the way gas does when space stretches. The simplest picture treats it as a property of space itself. Imagine a fabric that, when stretched, does not become sparse. Every new patch comes with the same built-in energy. The more space there is, the more of this energy exists. So its effect grows as the universe expands. For the web, the consequences are clear. In the early universe, gravity led. Matter streamed along filaments, clusters thickened, and the pattern sharpened. As time passed, dark energy's influence grew. Around 5 billion years ago, its push overtook gravity's pull on very large scales. Since then, expansion has accelerated, thinning filaments and increasing the distances between massive nodes. The skeleton remains, but the threads feel tension, as if pulled from both ends. We already see the first signs. Clusters that are tightly bound will stay together. Systems that are only loosely linked will drift apart. Superclusters that look coherent today will slowly unravel at their edges over tens of billions of years. On small scales, where gravity is strongest, structure is stable. On very large scales, where dark energy dominates, the pattern stretches. The web is caught in a long tug-of-war. Gravity weaving, dark energy unweaving. Mathematically, the simplest form of dark energy is Einstein's cosmological constant, a term he once added to keep the universe static. After Hubble's discovery, Einstein called that move a blunder. Ironically, the observation of acceleration brought the constant back as the leading explanation. Whether dark energy is truly constant or changes with time remains an open question, one of the deepest in physics. A picture helps. Imagine a grid of dots connected by elastic bands. Gravity is the elasticity that draws the dots together. Now inflate the whole frame. At first, the bands keep the dots near. As the inflation speeds up, the bands stretch thin. Only the tightest knots hold. That is the web's future in broad strokes. Dense nodes remain bound, while the connecting strands are pulled across growing voids until they become too faint to feed the hubs efficiently. Astronomers test this story by comparing the clustering of galaxies today with the patterns frozen into the cosmic microwave background. The measurements show that the growth of structure has slowed. Gravity continues to draw matter into filaments and clusters, but accelerated expansion limits how far and how fast large structures can connect. In that sense, the cosmic layout is crystallizing. No new superstructures on the scale of the largest walls are expected to form. Look far ahead, and the picture turns spare. As expansion continues, galaxies not bound to our region drift beyond our cosmic horizon. Their light stretches to wavelengths our instruments cannot detect. For observers in the deep future, only the local cluster will remain visible. The wider web will still exist in a physical sense, but the links will lie beyond reach, as if the universe had emptied out. The change does not violate relativity. It reflects the fact that space itself can expand faster than light, can cross it over vast intervals, placing distant regions forever out of contact. Along the filaments, the story will become one of dwindling supply. Gas will keep flowing toward clusters for a long time, but the inflow will thin as distances grow. Without steady resupply, star formation will fade. Galaxies will use up their fuel and settle into quieter states. Filaments will not snap like string. They will fade into near invisibility, too diffuse to act as effective highways. On smaller scales, gravity keeps working. Inside clusters, galaxies will continue to pass, tug, and merge. Over long spans, these interactions build giant elliptical systems, smooth, red, and massive. While the diversity of spirals and irregulars declines, the nodes persist, the strands recede. Isolation is the end state for the largest scales. Each cluster becomes an island, adrift in an expanding ocean with few landmarks. For any future skywatchers there, the dome of night will shrink. Galaxies beyond their own cluster will fall below detection. Without records from our era, they might believe the universe is small and static. Only in our present age do we see the web in full. Filaments spanning hundreds of millions of light years, nodes blazing with activity, and voids marking the spaces between. Some projections reach further still. Trillions of years ahead, most stars will have burned out, leaving white dwarfs, neutron stars, and black holes. Clusters will dim into swarms of remnants over yet longer spans. If current theory is right, even black holes will evaporate through Hawking radiation. In that distant epoch, the web will not just be faint, it will be gone as a visible structure. All of this depends on what dark energy truly is. If it remains constant, expansion continues forever, and large-scale connections weaken. If it evolves, the path could change. A few models predict a slowing that would let gravity regain ground. Others propose a big rip, where the expansion grows without bound and tears apart galaxies, stars, and eventually atoms. Current data favor a constant dark energy, but the door remains open to surprises. Whatever the fine print, the direction is the same: fading connection. The web we admire today will not last in this form. Filaments will stretch, clusters will grow more isolated. The busy exchange of matter will quiet. The design we see is a phase long by human standards, but still a chapter in a larger story. There is a quiet lesson here. Change is built into the universe at every scale. Stars form and fade. Galaxies grow and settle. Even the largest patterns evolve. The web's work, though, is already written into what exists now. The stars that shine, the planets that orbit, and any lives that may look up from those worlds. For the moment, we live in a fortunate window. The web is visible and measurable. Telescopes trace its filaments, surveys chart its nodes, simulations echo its shape. Dark energy's reach does not erase the picture instantly. It changes the balance slowly, over eons. Gravity and dark matter have already carved the main lines. Those lines will endure for ages before they thin beyond use. The shift in forces is real, but the pattern still stands, letting us study the universe in its most connected state. Dark energy's pull is both a challenge and an opportunity. It challenges us because we do not yet know what it is or why it exists. It gives us an opportunity because, right now, the web spans our view. We can read its layout and test our ideas about its growth. We are seeing a universe under tension, gravity's architecture stretched by expansion. The web is not a frozen statue. It is the balance of influences that began with faint quantum ripples, was shaped by dark matter and gravity, and is now being drawn wider by dark energy. The threads may thin and the nodes may drift, but the imprint is written across the sky we observe. As it stands today, the web is a network of filaments and clusters. Galaxies ride the strands. Intersections glow with crowded activity. Voids outline the design. Nothing in the cosmos is permanent in detail, so the web will change as time passes. The key question becomes how and on what schedule. On short cosmic scales, millions to billions of years, gravity still rules inside clusters and groups. On the widest scales, hundreds of millions of light years and beyond, dark energy stretches distances and slows the growth of new connections. Picture a dewy spiderweb at dawn. At first, every droplet hangs from a fine net. If you pull the frame wider, the threads thin. The droplets separate into isolated beads. So it will be with clusters and filaments. Bright nodes will remain. Long strands will become too faint to keep the traffic flowing. We already measure the drift. Farther galaxies recede faster than nearby ones. Over tens of billions of years, many will slip beyond the horizon of any given observer. Their light stretched too long to detect. The web will still exist beyond that edge, but not for those observers to see. For galaxies along filaments, connection will wane. Gas will continue to fall in for a time, then supplies will thin. Star formation will slow as fuel runs low. The highway remains on paper, so to speak, but traffic dwindles to a trickle. Within clusters, change continues by gravity's hand. Encounters, tides, and mergers build up large, smooth galaxies. Spirals give way to ellipticals. The nodes survive, but the web's long strands grow pale. In the end, each cluster stands alone, an island with its own history, and a sky that no longer hints at a broader network. Future astronomers there would need deep clues, or archives from our era, to infer that a grand web ever linked their world to distant hubs. All long-range forecasts depend on the nature of dark energy. If its strength is steady, expansion stretches on without end, and isolation grows. If it varies, the path may bend. For now, evidence points to a steady push. Either way, the lesson for the web is similar. Large-scale connections fade with time. The pattern we see today is a peak of visibility, not a permanent state. That thought is sober, but it does not reduce the value of what we have learned. It highlights the importance of careful maps and clear tests while the signals are strong. Before we could map the web with telescopes, astronomers tried to build it inside computers. If the laws of physics shape the universe, then we can write them as equations, set initial conditions, and let them run to see whether threads, nodes, and voids emerge from the rules themselves when the system is allowed to evolve. The cosmic web is not only a structure of space, it is a structure of time. When astronomers map its filaments and nodes, they are not simply seeing where galaxies are, they are seeing where galaxies were. Because light takes time to travel, distance becomes a timeline. A nearby galaxy shows a recent chapter. A very distant one shows an earlier page. In this sense, every deep image is a layered record. The same frame holds many eras at once, young systems shining from the edge of the visible universe, mature spirals in the middle distance, and close neighbors whose light left only millions of years ago. We do not look across the universe so much as back through it. This idea is called look-back time. If a galaxy is 10 million light-years away, we see it as it was 10 million years in the past. If it lies 10 billion light-years away, we see it when the universe itself was young. A sky survey, then, is not a simple map. It is a stack of time slices wrapped into one view. The filaments we trace at great distance are the filaments of an earlier web, thinner and less settled. The nodes that appear as bright clusters nearby are later stages of the same growth. The web is a moving target, and our measurements capture its motion by sampling different depths. Redshift is the tool that ties distance to time. As space expands, light's wavelength stretches, shifting toward the red. The amount of shift tells us how long the light has been traveling. In practice, astronomers take spectra spreading a galaxy's light into its colors and measure small fingerprints made by atoms and molecules. The positions of those lines act like marks on a ruler. From them we infer how far the light has come and how far back in time we are seeing. With redshift in hand for many galaxies, a three-dimensional map becomes a four-dimensional story. Because of this time layering, the web looks different at different depths. At large look-back times, galaxies are smaller, more irregular, and richer in gas. They form stars quickly and in bursts. As time passes, gas turns into stars. Supernovae enrich the gas with heavier elements, and gravity organizes shapes. Disks settle. Spiral arms appear. In crowded regions, mergers build big elliptical galaxies. The web's long threads funnel matter into the crossings, and the crossings grow bright. The peak pace of star birth across the universe, sometimes called cosmic noon, arrived roughly 10 billion years ago. Since then, the average rate has declined, even though many galaxies continue to make new stars. The web supply lines still feed them, but the rush has slowed. Light also carries clues about age. Young stars are hot and blue. Older stars are cooler and redder. By measuring a galaxy's overall color and its spectrum, astronomers estimate how long ago most of its stars formed. Heavy elements, built in stars and spread by explosions, imprint features in the spectrum too. From these, we learn how many generations of stars have lived and died. Taken together, color, spectral lines, and redshift, these simple signals tell a life story. When a galaxy's main growth happened, how fast it formed stars, and how its environment shaped it. Environment matters because time flows differently for structures of different sizes. Dense regions that later become rich clusters start forming early. They pull in matter faster. Their galaxies run through gas sooner and feel more encounters and mergers. Along quieter filaments and in voids, change is slower. Gas lasts longer. Spirals keep their disks. Over billions of years, the contrast grows. The web amplifies its own pattern. Busy hubs get busier. Quiet stretches stay sparse. Even the way we measure the web carries timestamps. Redshift surveys reveal fingers that seem to stretch galaxies toward us in the maps. These are not real shapes. They are artifacts of motion inside clusters, galaxies moving fast in deep gravity wells. On larger scales, a different pattern appears as gentle compressions along the line of sight, showing how flows fall into filaments and walls. Both effects remind us that a redshift map is part position, part motion, and altogether a record of change. Other signals write time on the web in different ink. The hot gas that fills clusters shines in X-rays. Its temperature and structure record shocks from past mergers and the steady rain of matter from filaments. Against the cosmic microwave background, that same gas leaves a tiny fingerprint known as the Sunyaev-Zeldovich effect, a slight change in the microwave light caused by energetic electrons in the hot gas. These marks tell us when clusters formed most of their mass and how often fresh material still arrives. They also show that hubs continue to grow by slow accretion even now. Strong gravitational lenses add another kind of clock. When a foreground mass, like a cluster, splits the image of a distant galaxy or quasar into several copies, the paths of light are different lengths. If the background object varies in brightness, those copies flicker with time delays between them. Measuring the delays tells us about distances and expansion, which folds back into the web's growth history. In this way, a blink of light becomes a ruler for time and space. Large patterns in the galaxy distribution act as timekeepers too. Baryon acoustic oscillations, faint relics of sound waves in the early hot plasma, leave a preferred separation scale between galaxies, a kind of standard ruler frozen into the web. By measuring that scale at different redshifts, astronomers watch how distances grow and how quickly structure assembles. These checks show a universe where gravity built the web early, and dark energy has slowed the growth of the biggest new connections in later times. The first pages of the story lie at even greater look-back times. Before the first stars, the universe held dark matter, thin gas, and a faint afterglow from the Big Bang. Small ripples in density grew until the first stars switched on, a period called cosmic dawn. Those early stars were massive and short-lived. Their light began to strip electrons from neutral hydrogen, changing the foggy gas into a clearer medium, a transition known as reionization. Distant galaxies from this era are dim and few, yet their collective effect changed the whole sky. The web at that stage was sketch-like. Narrow threads, small knots, vast smooth regions. As more stars and small galaxies ignited, the threads thickened, the nodes brightened. Reionization ran to completion. Later, larger galaxies took over as the main sources of light. Because the web's time structure is layered, we must be careful when we put its pieces together. A nearby filament and a distant filament in the same image are not the same thread at two places. They are two epochs of the web. To build a coherent picture, we sort by redshift, stack similar times, and watch how statistics change. How many galaxies of a given size, how strong clustering is, how much gas remains. In this way, we convert a set of still frames into a time lapse. Simulations help bridge the gaps. They take the measured early conditions and let gravity and gas physics run forward. We then cut the simulated volume into light cone views, mock observations that mimic how look-back time works. If the mock maps match real maps at the same redshifts and filament thickness, node masses, void sizes, we gain confidence that we are reading the time structure correctly. If they do not match, we learn that some part of the recipe is off: the nature of dark matter, the rules for how gas cools and turns into stars, or the feedback from black holes and supernovae. In that way, mismatches become guides for improvement. Seeing time in the web also means reading its fossil record. Inside galaxies, old stars carry chemical tags from earlier generations. The distribution of elements, carbon, oxygen, iron, varies with place and age. By mapping these patterns, we trace when gas flowed in along filaments, where it formed stars, and how outflows from supernovae and black holes carried material back out to the halo and into the surrounding medium. In clusters, the hot gas is enriched too. Its chemistry reveals that many stars formed long ago in smaller systems that later merged into the present hubs. The web's past is written both in starlight and in the gas between the stars. Even voids tell time. Because they are underdense, they expand a bit faster than average. Their sizes and shapes change in a way that depends on how structure grows and how dark energy pushes. By measuring void statistics at different redshifts, we can test models of expansion and see whether the cosmic push behaves like a true constant or shifts gently with time. In a quiet way, emptiness becomes a clock. Look-back time also changes how we think about cause and effect across the web. A flash from a distant quasar can light up gas along the line of sight, revealing a filament in absorption at the quasar's epoch. Nearby, a galaxy's outflow may be seen pushing into its surrounding halo in the present. The two effects can sit in the same sky frame but are separated by billions of years. The web is a collage of events unfolding on different schedules. To understand it, we align those schedules rather than relying only on the picture plane. Because the universe expands, distances between unbound structures grow over time. Yet bound systems, galaxies, groups, clusters, live under their own clocks. Inside a cluster, orbital periods are measured in billions of years. A galaxy disk rotates in hundreds of millions of years. Star formation and supernova feedback play out on millions to tens of millions of years. Black holes flare on shorter cycles still. Layer these clocks, and a node becomes a stack of rhythms. The web supplies matter on the longest beats. Local physics arranges it on the shorter ones. In recent years, deeper infrared observations have pushed the timeline further back. Very high redshift galaxies, tiny, low-mass systems with intense star formation appear in growing numbers. They mark the first threads of the web turning luminous. At intermediate redshifts, large surveys measure the slow decline of star formation and the growth of quiet, red galaxies whose stars formed earlier. Nearby, precision maps record the settled filaments and the well-fed clusters. Across this range, one message repeats: the web we see now was seeded early, grew quickly in its youth, and has been refining its pattern ever since. Time also shows up through delays inside lens systems, aging star clusters, and the travel of shock fronts along filaments. In merging clusters, bow shocks mark where gas has slammed together. Their positions relative to the galaxies reveal the sequence of events. Along some filaments, weak radio emission traces, aging cosmic ray electrons moving in magnetic fields. These are niche signals, but each one adds a small hand to the many clocks of the web. When astronomers speak of survey depth, they mean both faintness and time reach. A deeper survey gathers older light. A wider survey samples more environments at the same epoch. The best pictures combine both, wide enough to map the skeleton, deep enough to see back to earlier stages. With these, the web becomes a timeline. We can scroll forward in simulations, backward in data checking that each stage flows into the next without contradiction. All of this rests on simple ideas made careful. Light takes time, gravity shapes flows, gas makes stars, and expansion stretches distances. From these, a layered structure appears, not a single static net, but a living record of change. The map of the web is, at root, a diary. It keeps entries from many dates, written in the ink of starlight, X-rays, microwaves, and radio waves. By learning to read each script, and by placing each line on its proper page, We recover how threads grew, how nodes filled, and how the empty spaces widened as matter slipped away toward the edges. Light needs time to cross space, and across cosmic distances the time becomes huge. A galaxy 1 billion light-years away does not show us its present. It shows us how it looked when that light left, long before humans existed. A galaxy 10 billion light-years away shows a younger stage still, lit in an era when the first large clusters were only starting to grow. Looking at the cosmic web is like using a time machine. Every telescope works as an archaeologist of light. The cosmic microwave background shows a glowing fog from about 380,000 years after the Big Bang, a baby picture of the universe. Nearby galaxies show the recent past. Between those ends lies a long series of scenes, filaments tightening, clusters building, voids widening. Put together, these views form a timeline written in matter. Each strand of the web stretches across space and across billions of years at the same time. The web in this story is not frozen. It is still changing under the pull of gravity and the push of expansion. Matter continues to move along filaments. Gas slides toward nodes where galaxies gather and clusters grow. Observations of faint, distant galaxies, compared with careful simulations, show that this flow is ongoing. New stars are still forming from material delivered by the web. Even our Milky Way continues to draw in gas from surrounding streams, keeping star formation alive. In that sense, the web is not only a relic, it is an engine working today. Different epochs leave marks on the pattern. The early universe was very smooth. Tiny ripples, seen in the microwave background, grew into the first filaments. By about 1 billion years after the Big Bang, small galaxies had begun to appear along those filaments, turning on the first rounds of stars and feeding young black holes. By 5 billion years, clusters had thickened at the crossings, voids had drained, and the pattern began to resemble the lacework we map now. After about 13 billion years, the current age, the web is fully drawn at large scales, yet not finished. Filaments still bring in matter, clusters still gain mass, voids still empty out a little more. Deep views act like a photo album. Galaxies 10 billion light-years away look small, irregular, and busy with star birth. Closer galaxies look larger and calmer, shaped by mergers, star formation, and quiet settling over long times. Clusters at middle distances show how nodes grew from small groups into giant cities of galaxies. Even voids tell a story. They expand with time as matter flows out toward the surrounding threads. The web is not only an arrangement, it is a narrative with chapters. Computer simulations help us stitch those chapters together. We start with the early conditions measured in the microwave background almost smooth, with tiny ripples, and then let gravity and gas physics run. Filaments emerge. Gas falls into dark matter halos. Clusters build at intersections. In hours or days of computing, we watch billions of years of growth. The result looks like what telescopes see, which tells us the basic rules are right. These models can also run forward. They show how dark energy will keep stretching space, how large structures will grow more isolated, and how the pattern will evolve in future eras. This double nature, part history, part living system is what makes the web so compelling. It is ancient and new at once. The same filaments that carry the faint signal of early quantum ripples are still delivering fresh fuel for stars today. Every star we see owes its existence to that slow supply. Our sun and its planets formed because gas flowed along a filament into the young Milky Way long ago. The thread that once fed our galaxy is the same one that holds a memory of the beginning. It is tempting to think of the web as a sculpture etched into space-time, fixed and still. The truth is more like a set of rivers. Rivers look steady from a distance, but they are always moving. So are the filaments. Galaxies drift along them. Clusters swell where they meet. Voids hollow out further. On human scales, the pattern looks unchanged. Yet over cosmic scales, it is full of motion. A tree can seem still, but it grows, year by year. The web does the same, only on billion-year steps. There is a bittersweet side to our view. We live in a brief window when light from far galaxies still reaches us, letting us see the web across much of its span. In the far future, as dark energy speeds up the expansion, many distant galaxies will slide beyond our horizon. The web will continue, but we will no longer see it in full. Future observers may find only a local cluster in their sky, with little clue to the wider network that once linked it to others. That makes today's mapping feel like preservation. Each survey, each simulation, and each image becomes a record of the web at its most visible moment, billions of years from now. Such records may be the only evidence that this grand network ever stretched across the heavens. Threads of time run through every part of the pattern. They connect faint ripples in the early universe to the galaxies shining now. They tie the gas, still flowing into clusters, to stars that will light the future. They link past, present, and future into one long story about structure and change. When we look at the web, we are not only seeing space, we are seeing time, folded into the largest fabric we can measure. This view raises a deeper question about order and chance. At first glance, the web looks highly ordered. Galaxies are not scattered like sand. They trace lines and walls that cross empty basins. The scene looks built with care. Look closer, and you find that the web is also the child of randomness. The seeds were quantum jitters, tiny, unpredictable variations. Gravity and dark matter took those small, pattern-free ripples and shaped them into threads. So the web holds both sides. Chaos at the start, order in the result. What do we mean by order in this context? The web looks organized when we step back, but no galaxy chose its place. The pattern emerged from many small interactions, each piece following simple rules. A flock of birds draws a graceful curve across the sky without a leader. In the same way, the web self-organizes under gravity. The order we see was not imposed from above, it grew from below. Contrast matters. Vast voids lie between the filaments. Without the empty, the filled would vanish into sameness. The balance between full and hollow makes the pattern visible, like pauses in a melody. Order is not only the presence of structure, it is the relationship between presence and absence. The web shows that emptiness can be as important as what fills space. Perspective matters too. To us, the web looks intricate and beautiful. Is that beauty in the structure or in our minds? Up close, in a small region, the pattern can look messy. Only at large scales does it resolve into a clear design. A pointillist painting is dots from a few inches away and an image from across the room. The web teaches the same lesson. What seems chaotic at one scale looks ordered at another. Order and chaos depend partly on where we stand. Randomness played a necessary role in the beginning. The first density differences were quantum in nature. Without them, nothing would have formed. In this sense, noise became the seed of structure. We see this in many places. turbulence making eddies, genetic variation driving evolution, random grain in a system helping patterns to appear. The web is another case where disorder at a small level produces order at a larger one. Entropy tells us that the universe as a whole trends toward disorder. Heat spreads, stars burn out, systems relax. Yet within that trend, local pockets of order can arise and persist for long times. Galaxies, stars, planets, and the web itself are evidence that structure can grow and last, even in a universe where the average state drifts toward uniform heat. The web will not last forever in its present form. Dark energy will stretch distances. Galaxies will use up their fuel. Voids will deepen. But for now, the balance has produced the largest pattern we know. There is an irony in the scales. The largest visible structure came from the smallest kind of uncertainty. Quantum jitters far below the size of atoms, seeded filaments that span billions of light years. Scale is not a barrier to pattern. The line between randomness and design is not sharp. The universe blends them. This reflection invites questions about meaning. Does the pattern imply a purpose? Or is it simply the natural result of basic laws? Beautiful but indifferent? It can be both. The web did not form for our sake, yet it made galaxies. Galaxies made stars. Stars forged the elements that built planets and living things. Whether or not there is purpose, the web created the conditions for minds to exist and ask these questions. The resemblance between the web and other natural forms, neurons, rivers, roots, lightning, suggests that simple rules can lead to similar shapes at very different scales. Gravity follows paths of least resistance. Water does too. Networks form when systems must connect many points with limited resources. If these rules repeat across contexts, then the web is one version of a general way that nature builds complexity. The labels order and chaos may miss the point. What we are seeing is connection shaped by time, whether in soil, water, or sky. Another humbling note is how brief our open window may be. We live in a time when galaxies are bright and filaments still carry fuel. Far ahead, the web will fade into apparent emptiness as dark energy separates distant regions. Yet the record of the web will remain in what it built, in the stars that formed, in the planets that spun, and in the traces left in gas and light. The balance of order and chaos will continue to change form rather than vanish. So perhaps the clearest way to describe the web is as a union. It is order grown from chance, structure shaped by emptiness, permanence sliding into impermanence. The universe does not choose one side. It holds both. To call the web chaotic is correct. To call it ordered is also correct. The deeper truth is that what looks messy up close can be patterned from afar, and what looks ordered now began as noisy seeds. The web is a large-scale paradox made plain, order born from disorder. When we look at it, we see not a tidy diagram, but a living balance. It shows that the universe is neither a neat design nor a senseless scatter. It is pattern and accident at once. In that balance lies much of its appeal. The larger the view, the more the web invites language beyond numbers. Astronomers speak of filaments, clusters, and voids, yet the shapes also call to mind lace, fabric, and spider silk stretched across the dark. The web is not only a scientific structure, it is a pattern that welcomes metaphor, a design so wide and fine that words from science and art must work together to describe it. Imagine lace held against a dark sky. The lines are faint, but they form a steady pattern. The bright points are galaxies. The gaps are the wide, quiet spaces between them. Nothing here was placed by hand. Gravity and time arranged the pattern. Filaments meet at knots. Knots hold clusters. The design shows and hides at once visible where stars gather, invisible where dark matter leads. The appeal is not only in the strands but also in the openings that let the structure stand out. A second picture helps. Fabric. Think of a vast cloth stretched across space. Threads are filaments of dark matter, with galaxies stitched along them. Where threads cross, the weave tightens. That is a cluster. Where threads separate, the weave loosens. That is a void. This is not fabric for warmth or cover. It is the framework that allowed matter to collect, cool, and form stars and planets. The fabric of the cosmos is not just a phrase. Space really does carry a pattern: mass, motion, and gravity tied together across billions of light years. A spider's web offers the most familiar reference. A web looks delicate, yet it holds. The cosmic web is far larger and built by a different process. Still, the logic is similar. Beads of dew cling to silk. Galaxies cling to filaments. From far away, the pattern looks planned. In fact, it follows simple rules repeated over time. And, like a spider's web, this network both captures and sustains. It collects matter, guiding gas toward hubs where stars can form, and it continues to feed galaxies as long as supply lasts. Rivers give the web a sense of motion. Filaments are channels. Material flows along them. Gas and dark matter move toward the crossings, adding to clusters. Even when the largest flows slow, faint currents remain. Seen this way, the nodes are lakes, and the filaments are tributaries. The web carries hydrogen, helium, and dark matter, its version of a bloodstream. The image is simple, but faithful. Gravity sets the slope. Matter follows the path. Other comparisons appear because the pattern repeat is real. Foam. Filaments are the thin walls. Voids are the bubbles. Coral. Branching, porous, alive with points of light. Veins. Channels that move material where it is needed, forming a body scaled to the universe. These images work because many systems respond to similar constraints. Flows prefer efficient routes. Connections use limited resources. Simple rules produce network shapes at many sizes. These pictures help turn scale into something we can hold in mind. Lace can be folded. Fabric can be felt. A web can be traced thread by thread. Rivers can be followed from source to mouth. By borrowing shapes from daily life, the vast layout becomes less remote. The point is not to decorate the science, but to explain it. Under the words sits a clear rule. Gravity takes small differences and lets them grow. With time and repetition, a web appears. Pattern seeking is part of how people learn. We look for familiar forms. Clouds become animals. Starlines become figures. Spirals in shells echo. Spirals in storms and galaxies. The cosmic web, when mapped, invites the habit. We see cloth and river, web and vein. That instinct is not only playful, it can be a clue. If many natural systems echo each other in shape, perhaps they run on common principles. Flow along gradients. Conserve effort. Connect where it counts. Even the empty regions carry meaning. Voids are not blank in the sense of nothing at all. They are places with less matter than average, and that deficit shows the web more clearly. In art, white space makes the subject legible. In music, Silence gives rhythm room to breathe. In the universe, emptiness outlines structure. Without the voids, the map would smooth into gray. With them, threads and nodes stand out. Seen calmly, the web replaces the idea of a chaotic sky with a measured design. The pattern is not rigid or ornamental. It is the shape that arises when gravity and expansion act for a very long time on a nearly uniform start. Galaxies are not drifting without context. They sit on lines, and those lines converge. The map is wide, but it is not random. To picture yourself near that map, imagine gliding through a faint network. The lines are too thin to see with eyes alone. You sense them through the clustering of light. The stronger nodes hold many galaxies. The sparser lanes connect them. The space between is deep and quiet. Nothing here moves quickly to us. But over very long times, the flows are real. Galaxies slide along gentle slopes. Gas continues to trickle toward the crossings. A large pattern changes by degrees. Rivers make the motion easier to feel. If you trace a filament, you trace a flow. You follow faint gradients toward a cluster that gathers material from many directions. Currents do not rush. Their scale sets their pace. Where they meet, activity grows. Star formation, interactions, and mergers. Where they part, quiet returns. Yet connection remains. Even the thin paths tie distant regions together. In close view, the network looks organic rather than mechanical. A filament bends, a branch splits, a void rounds out and presses against its neighbors, like bubbles in a foam. A cluster holds a tangle of orbits, more like a living knot than a rigid joint. The resemblance to roots and veins is not an accident. All are solutions to problems of moving and collecting material in three-dimensional space. To stand back from such a structure can feel overwhelming. The Milky Way, large to us, is small in this frame. It is one bright system on one lane of a network with many lanes, yet the feeling need not be smallness alone. It can be placement. Our galaxy sits inside the pattern. Our star sits inside the galaxy. Our planet orbits our star. The chain of belonging is clear. The web also records time. Its shape is the long result of early ripples amplified by gravity. Its present motion hints at what lies ahead as dark energy pulls distant regions apart faster and faster. To be in the threads is to sit between memory and expectation. Light from far galaxies shows their past states. Gas inflow toward clusters projects their future growth. The scene holds both at once. The scale of the pattern encourages a slower mindset. The network did not form at once. Small differences accumulated. The system evolved without hurry. That pace can be a guide. Many processes run better a step at a time. Formation of stars, cooling of gas, settling of disks, even the way a careful map is drawn through repeated passes. A quiet method yields a strong result. The web's calm look does not mean it is empty of action. At nodes, galaxies pass and pull on each other. Gas heats as it falls in, then cools and forms stars, then heats again as supernovae and black holes return energy to their surroundings. Along filaments, flows keep the supply going. In voids, expansion wins, deepening the hollows. The pattern looks still because we view it on human time. On its own schedule, it is active. Seeing the web as a set of linked roles helps. Filaments, transport, nodes, storage, and processing. Voids, contrast and release. Dark matter, scaffold. Ordinary matter, content. Gravity, organizer, expansion, spacer. Each piece relies on the others to make a clear whole. If any part were missing, the product would change. No scaffold, no lanes, no hubs, no contrast, no visible pattern. The way we explore it adds to the picture. Telescopes map the light, surveys measure distances, lensing weighs what we cannot see, simulations test the rules and replay the growth. Together, they turn a guess into a chart. The chart, in turn, guides new measurements. The feedback between data and model is its own small network, built to study a larger one. The web also connects scales. A star forms from a cloud in a galaxy disk. The cloud's supply arrives along a filament. The filament's path follows a dark matter channel. The channel grew from an early ripple. The path from ripple to star to planet to life is long, but it is one chain. The Sun and Earth are late steps on a route carved out by the same forces that shaped the largest map we can draw. Standing inside the pattern, it is natural to ask what it means. Physics gives one kind of answer. The web is the outcome of gravity acting on small early differences inside an expanding space, with dark matter dominating the mass budget. But there is also a practical lesson that sits well with everyday experience. Connection matters, flows matter, contrast matters. Simple rules repeated over time make structure, often more effectively than forceful plans. The present epoch is generous to observers. Distant light still arrives. Filaments still connect visible nodes. We can measure the pattern before expansion hides much of it from any one vantage point. That fact gives urgency to mapping. Records kept now, images, catalogs, simulations will remain when parts of the network slip beyond view in the far future. The impulse to document is not only scientific habit, it is a sensible response to a changing horizon. If you walk back through the long story with a plain checklist, the scale settles. Early universe, nearly smooth with tiny ripples. Gravity amplifies the ripples. Dark matter forms the main scaffold. Gas flows along the scaffold and forms stars where it piles up. Feedback regulates how fast stars form and how gas disperses. Expansion stretches large distances and sets what can still be reached. Over time, filaments thicken, nodes grow, voids widen, then growth slows as expansion takes over on the largest scales. The pattern we see now is the mature stage of that chain. Placed within Laniakea, our supercluster basin, the local group sits on a modest sheet that feeds the Virgo cluster and other hubs. Farther out, larger nodes pull on our motion. Across the sky, walls show up as long ridges and surveys. Between them lie voids many tens of millions of light years wide. It is a layered neighborhood, and our address fits neatly. That address is not a small note to file away. It changes how we read a night sky. A bright galaxy is not a stray light. It is a signpost on a line. A cluster is not a random crowd. It is a hub. A gap is not nothing. It is a necessary interval that sets the rest into relief. If the pattern is familiar enough, it can ease a common feeling that a vast universe must be indifferent. Vast does not exclude structure. Structure does not exclude calm. Return now to the quiet images. The lace image survives because the contrast is real. Threads and openings. The fabric image survives because the weave is real. Crossings and spans. The web image survives because the function is real, catching and carrying. The river image survives because the motion is real, downhill, along a gradient set by mass. These are not ornamental phrases pasted over a mystery. They are sound guides to how the system works, translated into forms we know. It is useful to check where such images fail. The cosmic network is not fragile in the way silk is fragile. Gravity holds it in place far more firmly. It is not liquid in the way water is liquid. Flows are slow and shaped by cosmic expansion. It is not alive in the way veins are alive. No organ directs it. Limits like these keep the language honest. Within those limits, the pictures do good work. If you imagine one more drift through the map, set your pace to the system's scale. A filament that runs for hundreds of millions of light years does not hurry. A cluster that weighs a quadrillion suns does not snap. The times are long, the motions are sure. That steadiness is part of the appeal. It replaces shock with patience. It shows growth as a sequence of small steps rather than a set of leaps. The same patience appears in how we learn to see the pattern. The first hints came from sparse redshift lists and pencil beam maps. Then surveys grew broad. Then they grew deep. Then lensing added weight maps. Then simulations matched the maps well enough to trust the basic ingredients. Each step took years. Each step tightened the weave of evidence. The result is a clear picture that can be explained in plain terms without losing scale or care. Because the network is so large, we can use it as a stable reference for smaller stories. Star formation rates rise and fall inside galaxies, but the supply routes that feed them are set by the long slopes of the web. Merger histories vary, but the chance of meeting a neighbor depends on whether a galaxy lives in a hub, on a lane, or near a void. Local differences matter. Large-scale context matters too. Both can fit in one sentence. Where you sit in the web tilts the odds of what happens next. If you need one more practical angle, think of how the network supports measurement. The repeating scale, imprinted by early sound waves, gives a built-in ruler across many redshifts. The average shear from weak lensing provides a way to weigh the mass distribution. The hot gas in nodes marks where recent growth has been strong. Voids amplify signals of expansion. These tools let us read the same structure in different lights and check that the readings agree. The web, finally, is a good model of how order and chance work together. The start was noisy and small scale. The outcome is patterned and large scale. Nothing in the chain needed fine-tuning at every step. The rules were simple. The time was long. The system took care of the rest. That is not a message of fate or of emptiness. It is a message of process. Given the right conditions, connection appears. So the images of lace, fabric, web, river, foam, coral, and vein remain useful hooks as long as we hang them on facts. They help us remember that emptiness does not mean absence of structure, that distance does not mean lack of relation, and that the same physical ideas can shape forms from the scale of leaves to the scale of superclusters. They also soften a hard truth about visibility. The present is a good time to see the network. The far future will not be as generous from any one place. That makes measured attention now a sensible choice. Set all of this next to a simple scene. A sky, a band of faint light from our disk, a few smudges that are nearby galaxies, the rest too faint to pick out with unaided eyes. Behind that calm view lies the network we have mapped, the paths along which material has moved, and the hubs where it has gathered. The map is not a decoration. It is the framework that explains why the sky looks the way it does, and how it will change in the longest terms we can test. If the picture invites a quiet response, that is fitting. The network does not need grand words. It needs careful ones. Filaments are paths of matter shaped by gravity. Nodes are the deepest wells where many paths meet. Voids are the wide regions in between. Dark matter sets the main outline. Ordinary matter fills and shines. Expansion stretches the wide spaces faster than gravity can bridge them on the largest scales. Within that outline, galaxies form, live, and age. To sit with that outline is to feel a form of steadiness. We live in one small part of a large, connected layout. The layout changes, but slowly. It holds both presence and pause. It shows that structure can arise from simple starts without constant pushing, and it leaves room for the plain comfort that comes with a good map. We know where we are in a system that can be described clearly. Picture, one last time, the long lines crossing deep spaces. The lines are not perfect. They bend and branch. They are strong without being rigid. They hold many lights without noise. They lead to crossings that shine and to spaces that rest. From close up, the details fill the view. From far away, the pattern is easy to recognize. Both views are true, and together they make the design legible.